Morning, students. So, the topic for today is based on DC motors, that is, the starting of DC motors, and why do we need to a starter while starting a DC motor. And there are two different types of starters also, 3-point starter and 4-point starter. So, I'll be explaining the 3-point starter also. So, coming to the figure, you know that this is the figure of a DC shunt motor. So, for a DC motor, we know the EMF equation will be V is equal to EB plus IARA, and the armature current IA will be given by V minus EB by IARA. Like Kirchhoff voltage from K, by applying KVL, you can get the answer. And also we have the induced back EMF will be, the back EMF in a DC motor will be P phi NZ by 60A. So we know that at the time of starting, the speed will be zero, then the back EMF will also be zero, then the armature current IA will be V minus RA, that is V by RA. So the starting current, the armature current at IAS means armature current is starting. Armature current will be V minus RA. So let's assume that the voltage, of course, you know it will be 230. Then the armature resistance will be very low value, like 0.5 ohm. Usually we represent that in per unit, but since you are not familiar with the per unit system, let's consider it in ohm also. So RA will be 0.5 ohm. So then IAS, the starting current will be 230 by 0.5, which is 460 ampere. So you see, at the time of starting, the armature current is going dangerously very high. That is up to 460 amperes. This is a very high current and can affect the DC motor and can even destroy the brushes, because it can lead to heavy sparking, and this can this can destroy the brushes because it's a very high current. So we are supposed to have a mechanism to control the starting current. So when the motor starts, so after the motor starts, it begins to gain speed. So the speed will be increasing. So as the speed increases, the back EMF also increases. So IA is equal to V minus EB by RA. So as IB increases, V minus EB decreases. So armature current decreases. So we understood that at the time of starting, the armature current will be dangerously high, that is n is equal to 0, because at that position n is equal to 0 and eb equal to 0. So IAS, that is armature starting current, will be V minus RA, and RA is a small value, and that because of that the current will be dangerously high, even 100 times. But as the speed increases after starting, back EMF EB also increases and the armature current begin to decrease. So that concept you understood at the time of starting and after starting when the speed increases. And another equation we are familiar is like T is proportional to flux into IA, and also you know that the flux for shunt motor, the flux depends upon the field current, the field winding. Okay, so we can write T is proportional to IF into IA. So we know if IF so in the beginning, if you are giving a reduced voltage and the voltage is being increased gradually only, so as the voltage decreases, the field current IF also decreases. That is, if the voltage is less, then the field current IF will be less. So if the IF is less, then the torque T will be less. All comes from this equation. So if IF is less, the torque T will be less, and when the torque is decreased, motor will take more time to start. That is, dangerously the current will not be high. So we understood that initially the flux phi should be a rated flux, so that the torque is not affected, and the current IA should be limited to 1.5 to 2 times. So the starting torque will be limited to 1.5 to 2 times of the rated torque. So we use starters where we insert resistance in the armature circuit and go on reducing so in order to control the armature current from going dangerously high, we introduce starters. So two types of starters are 3-point starter and 4-point starter. What we do is we insert resistances in the armature circuit and we will gradually go on decreasing them. So at the time of starting, we should have a high resistance, and when it comes to run, that is fully run at full load, then the resistance should be decreased. That's what we do. That's what we do. So for a 3-point starter, this is actually the figure of a 3-point starter. We will have a overload coil, and then we have a soft iron here. Then we will have a NVC, which is a no voltage coil, and then we will have a stud here, and this is the handle, and we have a soft iron attached to it. And here, this is also made up of soft iron. This is the armature, this is the field winding, and this is the supply line voltage that it is applied. So what the reason why it is called 3-point starter is because of the 3 points. The 3 points are actually line terminal, which is connected to the positive voltage. Line terminal means here line terminal which is connected to the positive voltage. This is 1 point, and then we have the armature terminal. This one, A and F. We have A, which is the armature terminal, which is connected to the armature coil, and F is the field terminal, which is connected to the field coil. So these are the 3 points. So initially in off position, initially the system is in off position, when the machine is in off position. When the supply is on, initially the current will pass through the overload coil. It's actually called OLC as well as OLR. Sometimes we call it overload coil, or sometimes we call it as overload relay. So initially the current will pass through the OLC, and NVC is the no voltage coil, and the resistance value of NVC will be very less. Our NVC is a very less value. So in armature current, so in an armature circuit, initially the handle will be at position 1. So check the figure. When the handle is at position 1, the current coming will be going like this, and it will go like this, and it will go through the field winding. But our requirement is to reduce or restrict the armature current. So armature current means all these resistance will come. The current go to the armature will be, it will go like this, it will go like this, and it will come and it will go to the armature. So what will be the armature current? So armature current IA will be equal to voltage by divided by all these resistance. R1 plus R2 plus R3 plus R4 by plus RA, armature resistance also. See, at the time of starting, it will be V by R1 plus. So all resistance together, if we call R, it will be V by R plus RA. So that I will be very less. Then after that, then it again gains speed gradually, and when it reaches 0.2, it will be that the current will be little more high. After that, current will be then again current will be little more high, and when it reaches the run point, it will be taking the full load current. So gradually only the current is increasing by when we are reducing the resistance. So, you know, by Ohm's law, the current is inversely proportional to the resistance. So as the resistance decreases, the current will be increasing, and finally it will be at the run position. So construction wise, we can say that the starter is nothing but a variable resistance. See, here we are just changing the resistance, and we are getting the value, like we are getting the current. So it has 3 points, just like I2, and the contact points are called studs. So these are all the contact points, 1, 2, 3, 4, 5. So all these points, we call it as studs. Okay, so L is connected, that is the line is connected to the OLC, that is overload coil. Other end of the OLR is connected to the conducting part of the starter handle. It also has a spring. The spring actually helps in bringing the handle back to the old position during de-energization. So it is when the machine is de-energized, then this handle should come back to the old position. No, because if it stays here, when suddenly if power comes, means then the current will be dangerously high, because when we restart, we need the same process to happen again. That is the gradual decrease of resistance. So the spring helps in bringing back the handle to the old position, because this is soft iron. So at the time of full load, at run position, the both will be attached together, and they will stay there during energized condition. When it is de-energized, the handle should come back. That's why we have a spring here. So OLR and NVC actually acts as two protective devices of the starter. So finally, when the handle is at run position, the entire system is eliminated, just like I told you, and the motor runs at the normal speed. And NVC, its supply to the field winding is derived through the no voltage coil. That is, yeah, because here you can see that the supply to the field winding, it comes through the no voltage coil. So OLC and NVC, they are actually acting as two protective devices. So overload coil means when the current is dangerously high, the voltage will be passed through the overload coil, and it helps in protecting the device. So that's about 3-point starter and why we need a starter. I think for you people, the more important thing is why we need a starter, and 3-point starter also you should draw. You should draw the diagram and you should understand. So today's topic is why we need a starter and what is a 3-point starter. Hope everybody understood it. Thank you.